Okay, so we'll start the recording and we can get started here. Uh, Before we start tonight's lecture, does anybody have any questions that you'd like to ask from the last lecture? Okay, so start tonight's lecture, lecture 3. Gosh, I think I did. This should be posted to Blackboard. So you have a version of this presentation that you can look at beforehand. And okay, so tonight we're going to talk about flexural analysis of beams and get into some of the real mechanics of designing concrete beams. Reinforced concrete is designed by what's known as the strength design method. Strength design compares a reduced nominal capacity based on material mechanics to a factored load design, where a phi factor is a number less than 1 that represents a resistance factor to account for probabilities that the capacity is short of what was expected. And Mn represents the nominal flexural capacity of a reinforced concrete beam found from mechanics of materials. So I kind of making a big deal about this at the very beginning to compare that concrete is and has been for some time now designed by a strength design method, as opposed to what you might have heard from other classes or other materials is the opposite of that, is the allowable stress design method or allowable stress design. And really the difference is, and I'll get into it in a little bit more detail, but just from the basic point of view, the difference is allowable stress design says use the loads that you think you're actually going to have and compare them to some allowable stress in the material. Strength design is use a factored load, not the load you actually think is going to be there, but some load factored up to account for safety. And then you compare that factored load to what's known as a nominal strength, or your best guess at if you were to actually test this beam, where would it break? Where would it fail? And then we have a phi factor on the nominal capacity to account for that the beam in practice might have some unexpected shortcomings, material strengths or workmanship, things like that. Okay, so does that make sense? Just a very quick comparison between strength design and allowable stress.
Professor, when you say nominal, is that
Uh-huh.
like what you're expecting out of?
Yes, yes. Yes, good question. And we use that term a lot in this course, a nominal capacity. So a nominal capacity is what you would expect if your materials are what you assume them to be. In other words, if you assume that the rebar is going to be 60 grade rebar, you assume it's going to have 60 KSI before it yields. In the real world, it may be anywhere from 60 to 78 KSI. So you could have rebar that's actually much stronger than you assumed. And by the same token, if you prescribe that you want 6,000 PSI concrete, you very well may end up with 7,300 PSI concrete. So the nominal capacity is the capacity of an idealized beam that has material properties exactly as you prescribed, 60 KSI, 6,000 PSI, and that sort of thing. Which we have to assume, because if we call for 6,000 PSI concrete, you can't assume you're going to get 7,300 or really anything more than what you called for. Does that make sense?
Yes, thank you.
Okay, great. So we're going to use these terms, and I'm probably skipping ahead a little bit, but nominal is the strength you would expect if everything was built perfectly with exactly the material properties that you assumed. That's the nominal capacity. The allowable capacity is the nominal capacity that's been reduced by this phi factor. So that's going to be the difference between when we say a nominal capacity and an allowable capacity. The allowable capacity is multiplied by this phi factor. Okay, so the next point, MU represents the factored or increased demand from anticipated loading. Factoring varies based on the source of load and is derived from statistical probabilities. Next lecture, lecture 4, is going to dive into that a lot deeper and talk about exactly what the factors are, how you get the factors, how you combine them, how you look at them. That's all the next lecture. Just suffice it to say for now that MU represents a increased or factored load, and we're trying to design a beam that has a capacity, an allowable capacity, at least as strong or stronger than MU, the factored load. Okay, so strength design is based on a comparison of phi mn greater than in MU. And at the end of the day, at the end of every one of your homework problems or test problems or in the real world, uh, as a practicing engineer, this is your final step. Whatever it is that you have done to get into the ballpark or estimate how much steel you need or use the tables or equations, whatever it is that you use to come up with a reinforcing strategy, you have to do a final check to be sure that the allowable strength, phi times mn, is the allowable strength is greater than or equal to the factored load. So I'm always going to bring you back to this equation here. There's going to be a lot of problems where you're going to have to design a beam when you don't know how much steel there is, or maybe you don't know how deep the beam is, or you don't know how deep or wide the beam is. There's all these different scenarios of design, but whatever tools you use to come up with a reinforcing pattern, you always have to make sure you do this final check to be sure that what you've come up with is truly stronger than or equal to the demand.
Professor, are we multiplying by phi again as a factor of safety?
Yes, you are. Yes, you are. Uh, yeah, I'm sorry. It gets a little, because I'm going to get into that next lecture. The load factors and the resistant factors I'm going to cover in the next lecture. But you're absolutely right. What we do is we take the nominal capacity and we knock it down a little bit. And how much we knock it down depends on what it is we're looking at. So for flexure, we'll knock it down to 90%. For shear, we'll knock it down to 75%. So how far we knock it down depends on various different things, but it varies depending on what you do. So the nominal capacity is going to get knocked down by a phi factor. And at the same time, we're going to take the loads that we really think are going to be on the structure and we amplify those by load factors. Does that make sense?
Yes, thank you.
Okay. Okay, so just a little bit of history. Reinforced concrete was originally based on a working stress design, WSD. In ACI 318 in 1956 first included the ultimate strength design as an appendix. So basically everybody was using working stress design, but they came up with, you might get some better values. You get better efficiency and economy if you use a strength design. and they put it in the appendix. ACI 318 1963, ultimate strength design was presented equally with the working stress design. ACI 318 1971, ultimate strength design became the primary design method with WSD redelegated to an appendix. Stayed there for a long time, if you notice. That's 31 years. So ACI 318 2002 removed the working stress design method from the code. Gone. ACI 318 2002 also saw the load factors revised to match the ASCE 7 factors. I actually started practicing in 1995, so I saw these changes. I remember when 2002 came out, and that was actually pretty nice, because what was going on at the time is that various materials were using working stress design. Steel in the LRFD world was using factor design, but their factors were not the same as concrete factors. So you can imagine the headache, the nightmare of, picture a concrete column built on top of a concrete footing that has a steel column coming down on top of it. So the steel column has LRFD load factors. The concrete column, you have to convert them all over to ACI load factors. And then you go down into the concrete footing, and the soil is designed using working stress design. It was very complicated. So this was a huge improvement, 2002, where basically ACI, the steel industry, the wood industry, everybody just said, all right, fine, we're all going to use ASCE 7 load factors. Okay. So now we're going to talk about the actual beam design and how we come up with our beam design equations. As we mentioned before, concrete follows a fairly linear stress strain curve with a slope of E sub C up to about Fc equal to 0.4 F prime C. So up to about 40% of the strength of the concrete, it's following more or less kind of a straight line, which is good, because then we can use that to predict deflections and cracking and other serviceability issues. But at higher stresses and strains, the concrete is considered plastic, and expressions must be developed to capture this behavior. So if I look at the side view of a concrete beam, top of the concrete beam, here's your steel at the bottom of the beam, and I have some applied moment to it. Then if I look at the strain condition, the concrete at the top of the beam is in compression. So it has a strain defined by code as 003, and the steel towards the bottom of the beam is in tension. It's on the other side. And the strain, as we said last time, is a linear function. So we draw the strain condition. At failure, ACI 318 section 22.2.2.1 prescribes the maximum strain as 003. My hope is, when we do this presentation, I'm going to be quoting these ACI sections throughout this course. And my hope is that when you download this presentation and you can review it at your own leisure, you can use these as reference points. And you can go back to your ACI code, look that up, and say, oh, yeah, okay, well, that's why that is. That's where that came from. And so, again, that's my hope of quoting all these chapter and verses for you, is that you'll have this as a reference, and you can look back later and see how and why things come to be. Also, ACI 318, in many of these provisions, the actual code provisions, which is like a legally binding document, we have to follow these provisions, is on the left-hand side of the code. On the right-hand side of the code in a different column is commentary. So a lot of these clauses and provisions have some commentary to the side. So if I start getting into more complicated procedures and I give you where you can find it in the code, then you can look up the commentary next to it and get more information or some clarification as to how you're supposed to use that provision. Okay? So ACI 22.2.2.1 prescribes the maximum strain as 003, and that's what we're going to use there. This really becomes the anchor for us to be able to solve everything else going on in this beam. ACI 318 section 22.2.1.2 says that the strain in the steel or at any other location is proportional to the distance from the neutral axis, as labeled distance C from the top of the beam. So in this illustration, the neutral axis is defined as the point where you have zero strain, zero stress, zero strain. And the common symbol that we use for that is from the top of the beam to the neutral axis is labeled as C. And you'll see that consistently throughout the whole course. Concrete design always uses little c to designate from the top of the compression to the neutral axis. Do I have any questions yet? Okay. ACI 318 section 2.2 defines epsilon sub t as the strain in the layer of steel furthest from the neutral axis, closest to the bottom of the beam. Epsilon s is strain at the centroid of the steel. Okay, so this could be confusing. In this illustration, I only have one row of steel. So therefore, epsilon sub t and epsilon sub s are the same value. They're at the same location. But if I had multiple layers of steel here, then epsilon sub t is to the center of the lowest layer, whereas epsilon sub s is to the centroid of all the steel.
So could you repeat that one more time, please?
Sure. In the illustration, I only have one row of steel.
Right.
So epsilon sub t is the strain at the center of the lowest layer, which if you only have one layer, that's the same layer. So if there's only one layer, then epsilon sub s and epsilon sub t are the same thing.
Okay.
If you have multiple layers, epsilon sub s is at the centroid of all the steel, epsilon sub t is at the centroid of the lowest layer of steel.
Okay, so epsilon of t is the strain at the center of the lower steel.
Yes.
Right.
Yes.
And then epsilon of s is the centroid as the like of the whole. Okay.
Yes, you got it. Okay. ACI 318 section 9331 prescribes the minimum strain for epsilon sub t as 0.004 inch per inch, thus mandating that the steel has fully yielded at the point of concrete compressive failure, because the concrete, as we just said, is going to fail at 0.03, and the minimum strain that you find for epsilon sub t has to be 0.04. So the steel will always be yielding when the concrete crushes. That's the point of this. ACI code mandates that your steel is yielding when the concrete crushes. The distance from the top of the beam to the centroid of the flexural steel is labeled as D, as you see here. This is a common symbol. So it will always be D from the top of the beam to the centroid of your steel. If it's to the centroid of the lowest layer, then it's d sub t, same as epsilon sub t. Okay, now I've added in here a stress diagram. This was strain. Now we have stress. So the stress diagram, I've got some concrete stress, I've got a concrete resultant, and I've got a tension resultant as shown here. ACI 318, section 22.2.1.1 states that equilibrium must be maintained. Thus, tension must equal compression. And this is just straight out of mechanics of materials. You have to have equilibrium. So the resultant of all the concrete and compression has to equal exactly the resultant from all the steel in tension. Okay. ACI 318, section 22.2.2.4 allows for the Whitney stress block assumption to be used to approximate the summation of compressive stresses at epsilon sub Cu equal to 0.003 inch per inch. Okay, so remember last lecture, and I showed you how to go through a fairly complicated way to come up with this parabolic stress diagram, and then we use integrals to add it all up. What ACI says, you can still do that. It doesn't say you can't do that. But what it also says is instead of using integrals and adding up functions of concrete stress, we can use what's known as the Whitney stress block instead. The Whitney stress block uses this block. It's a rectangular shape. And what it does is the area or volume of this rectangular shape equals a compressive value very similar to, if not exactly the same as the integrals that we did before. But it's far, far simpler. So the Whitney stress block states that the effective stress of the block is assumed as 0.85 F prime C. So again, instead of the shape that we had, here I can draw it on here, instead of last time we had a shape that looked like this, and we were integrating this shape, instead of that, we can use a very simple rectangular shape where the stress is equal to 0.85 F prime C. Okay, diagram, there's, why is the strain concrete steel represented as triangles? Okay. Okay, I have a question. Let me try to answer this question. So this diagram is a strain diagram. And strain is always linear. So the strain, if you remember from mechanics of materials, strain is related to stress by Hooke's law. And stress is related to the moment by the distance c from the neutral axis divided by the moment of inertia. So let me see if I can text. We had that equation, sigma is equal to my over I from mechanics of materials. So m is constant for the whole section. M is this mx. I, the moment of inertia for this whole section, is constant. So the only thing that changes is y. Y is equal to 0 at the neutral axis, and y is equal to its maximum values at the top or bottom of the beam. So if the stress is 0 at the neutral axis, the stress is maximum at the top or bottom of the beam, then the strain is going to be maximum at the top or bottom of the beam. So the strain is being represented by the distance from the vertical axis here. It is maximum at the top or at the bottom. And then the strain is linear from this, let's see, from this point to this point, you draw a straight line. And what that tells you is what the strain is at any given location on the beam due to this moment. That's why it's a triangle, is because it's linear. And what you can get from this strain diagram is, say I want to know what the strain is right there. What's that strain? Well, I can use similar triangles. If I know what this strain is, and I know this strain is 0 here, and I know this distance is c, then I can get the strain at any other point. Yes, yes. Except the stress is not linear, the strain is linear. Stress is not linear, but the strain is. So if the strain is linear, the stress is shaped like that. It's parabolic. And we don't want to do this. That's the whole point of this conversation. I don't want to work with this stress. That's too difficult. I'm an engineer. I want an efficient solution so I can get on with my life. So I'm not going to use this realistic version of the stress. I'm going to use this approximation, the Whitney stress block. Okay? Is everybody up to speed? Any other questions?
So the block is representing stress.
Yes.
In the third figure?
Yes. Yes.
Okay.
This is stress. So, and that's an excellent question. So as I just said, the stress in the concrete looks like this. And I'm going to take this stress and use this stress instead. The centroid of this stress is right here someplace, and the centroid of this stress is right here, same place. The volume of this stress is equal to big C, the compressive force, and the volume of this stress is equal to big C, the compressive force. So if I can come up with a simplistic rectangular assumption for stress that is far easier to solve for and work with, that gives you the same compressive resultant at the same location, then why bother with this one when we can use this one? Does that make sense to everybody?
Professor, and this represents the stress along the cross section of the beam, is that correct?
Yes. Yeah. I could try to do this. This is a attempt at an isometric. So if I look at this isometrically, then that Whitney stress block looks like that. See, so there's a volume to this. The magnitude of the stress is 0.85 F prime C, and it's constant. It doesn't change over the depth. We assume the whole block is at 0.85 F prime C, and it's across the whole width of the beam, and is across a depth equal to this little a that we're going to talk about in a minute. Does that help?
Yes.
Okay. Okay, so the first part of the Whitney stress block assumption is that let me erase this so you can see it more clearly. The assumption is that the stress is uniform over the width, over the height. This whole block has a uniform stress of 0.85 F prime C. Okay. And then the next step, I guess I have to erase this because I added this diagram. The next step is, this is a diagram looking into this space here. So you can see that the stress block is a depth A and it's a full width B. And the centroid of that stress block is located at A/2. If A is the whole depth, then the centroid is in the center of that, or halfway. This uniform stress is distributed over the width of the beam B and over a depth equal to A. ACI 318, equation 22.2.2.4.1 defines that A is equal to this value beta 1 times C, where beta 1 is a factor based on a concrete strength and C is the distance to the neutral axis. So here's C, and C is something that we're going to solve for or iterate for, or in some way, shape, or form. We're going to figure out what C is. A is defined as a fraction of C, and that fraction depends on the strength of the concrete. Okay, so if you have concrete between 2,500 psi and less than or equal to 4,000 psi, beta 1 is equal to 0.85. If you have concrete between 4,000 and 8,000 psi, then beta 1 is this interpolation. This is basically just a linear interpolation. And if you have F prime C equal to or greater than 8,000 psi, then it just levels off to 0.65. Okay, so what this means is A here, if your concrete is at 4,000 or less, A is equal to 0.85 times C. And then you use these other ones like so. We also, in lieu of using the interpolation, you can go to the back of your textbook and I'll find it here in a second. And go to table 8.7 in Appendix A, table 8.7 on page 598. And for concrete strengths of 3,000, 4,000, 5,000, or 6,000, it tells you what beta 1 is right there at the top of the column. That's another way to get to that answer. Okay, so do I have any questions about the compression block?
Professor, we pretty much use the beta 1 in that equation to find the A because we'll know C before going to find A.
Sometimes. That's a great question, but we actually will work it both ways. Sometimes we know what A needs to be because it has to balance out the tension steel, and we'll find C by dividing A by beta 1. But other times we'll solve for C first, and then we'll find A by multiplying it by beta 1. So we're going to work it both ways. So please keep that in mind. This A equals beta 1 times C can work both ways. You might, sometimes you know C, sometimes you know A, and then you use it to find the other one. Okay, ACI 318, section 22.2.2.2 prescribes that the tensile capacity of the concrete to be neglected in strength calculations. Okay, so what that means, here's my beam again. Everything on this side of the triangle is in compression. Everything on this side or below C is in tension. This is basically just the code version of telling you what we already know. ignore any tensile capacity of the concrete for your strength calculations. Because the reinforcement is assumed, actually prescribed, the yield at epsilon CU equals 0.003 inch per inch. In other words, when the concrete crushes, the steel has to be yielding. That's a code mandate. Because of that, the tensile force is equal to the area of the reinforcement multiplied by the yield stress. And this makes our lives a lot simpler. If you recall from what we talked about in the last meeting, steel, the stress strain for steel is a bilinear. Looks like this. So if your strain is in the elastic range, you have to solve for what the stress is. If you know what the strain is, you have to solve for what the stress is. But if you're in the plastic region over here, then it doesn't matter what the strain is. We don't even need to worry about what the strain is really, because the stress has to be the yielding stress. And that makes the calculations a lot simpler, because we know that the stress in the steel is going to be the yield stress. Now that's going to get a little more complicated when we start talking about compressive steel. Steel at the top of the beam that's in compression, that's not going to necessarily be true. But for steel in tension, the main flexural steel in tension, that will always be true. So in equation form, T, the tensile force, T, is equal to the area of steel times the steel's yield stress. Using the Whitney stress block, the compression force is equal to the effective stress multiplied by the beam width by the assumed depth. So I'm saying here is C is the summation of the stress across a width of B and a depth of A. So C is equal to the assumed stress, 0.85 F prime C, times B times A. That's this area here, which is also equal to 0.85 F prime C, B, and then substitute for A, beta 1 C. The compression force C is assumed to act at the centroid of the compression block, or A over 2, down from the top of the beam. Again, D is the distance from the top of the beam to the center of the steel, as labeled right here. For beams with multiple layers of reinforcement, D is measured to the center of gravity of the total tension steel, as we mentioned before. Were any questions on that last slide?
No.
Okay. So, since the sum of the forces in the x direction has to equal 0 for equilibrium, T must equal C. T is equal to ASFY, C is equal to 0.85 F prime C, B times A. And here's my diagram again. So C is the stress over the area A times B, and T is area of steel times yielding stress. Solving for little a is equal to ASFY over 0.85 F prime CB. If we sum moments about C, remember the resultant C is at the centroid of the compression block. So if I sum moments about C, then my nominal capacity is T times the moment arm. The moment arm is D minus this little part right here is A over 2. So the moment arm of the steel to the compression is D minus A over 2. substituting T ASFY. So the nominal capacity is ASFY D minus A over 2. And I can substitute for A this expression here. So Mn is equal to ASFY D minus ASFY over 2, because that was A over 2, 0.85 F prime C B. And finally, we get to the nominal flexural capacity is ASFY D minus ASFY over 1.7 F prime C B. This is what's known as the basic equation for singly reinforced beams. So this is your check. Remember I said earlier, regardless of how you get to your design solution, regardless of how you get there, you always have to do a check that your allowable capacity, which would be phi Mn, is greater than mu. And this is how you would calculate your nominal capacity. Also, please note that this is only for singly reinforced beams. I've had a lot of confusion about this in the past. I present this equation, everybody goes, yay, we finally got to something I can use to solve my homework. There it is, thank you very much. And then we start talking about T-beams, we start talking about compression steel, doubly reinforced beams, and columns, and other more advanced topics. And my students want to keep using this equation. Do not do that. This equation is only valid for singly reinforced beams. Okay, does that make sense?
Professor, how about phi? Would it be given?
Phi, we will get to phi. Yes,
Okay.
yes. That's like almost coming up in a minute.
Okay.
But no, I have to throw something at you and then something else at you, and then it doesn't really all come together until the end. So I apologize, but you got to start somewhere. So yes, phi is coming.
Okay.
So this is, as we said before, this is the nominal flexural capacity. Nominal. And that's what the little n stands for, is nominal flexural capacity. When we talk about phi in a minute, then we will have the allowable flexural capacity. Okay, so let's do an example. Let's find the nominal flexural capacity of the following beam. Here I have a beam that is 18 inches wide, 30 inches deep, and the steel is located 2.5 inches up from the bottom of the beam. F prime C is 6,000 PSI concrete. My steel is 4 number 8s. And in all of the times I've taught this course before, I didn't have to put this right here because pretty much all steel was grade 60. So we didn't have to explain that. But I'm going to try to be more specific and say A706 grade 60. Really, out of this expression, all you really need to know is grade 60. That means Fy is equal to 60. That's what you need to know. And if during this course, I do not specify A706 or grade 60 or grade 80 or whatever, if I just say 4 number 8s and I don't say anything after it, please assume we're talking about 60 KSI steel. It is by far still the most common steel out there. So if I forget to tell you, assume 60. Okay, so our solution. You have to go to either your first lecture notes or the back of the textbook or the back of your ACI code. Those are your 3 resources that you can go to. And look up the area for a number 8 bar. A number 8 bar is 0.79 inches squared. I have 4 of them, so 4 times 0.79, I have 3.16 inches squared of steel. T is equal to ASFY, 3.16 times 60 KSI, because it's grade 60, equals 189.6 kips. That's my total tensile force. D is 27.5 as labeled here. B is 18 wide. And so my nominal capacity is, again, remember the equation is ASFY D minus ASFY 1.7 F prime C B. And this equals 5,018 kip inches, or divide by 12 to get to 418.2 kip feet. Okay, here's what's cool. Remember last lecture?
So I just have a quick question.
Yes.
Where did FY come from? The value 60?
Came from right there.
Oh, okay, right there. Okay.
Okay. So remember last lecture towards the end, and I gave you a function for the stress given strain, a stress strain function for concrete. I said this is just a model. It's not perfect, but it's a fairly good model. And then we integrated it, and then we integrated it again with XDX to find the centroid. And then at the very end of that whole problem, after all those integrations and functions of X and this and that and everything else, we ended up with 418.2 kip feet. Because if you remember, this was the same beam.
Professor,
Yes.
should that equation be 60 instead of 6 KSI in the parentheses?
There?
Yeah, should it be
No.
60, right?
No.
FC? Isn't it FC?
That's F prime C. Watch your units. It was given as 6,000 PSI.
Oh, okay, not from the steel, right?
No, the
That's
steel.
That's the design strength, right?
Okay, well, this is a very good question. Let me finish my comparison, then I'll get back to your question.
Yeah.
So last lecture, we used a bunch of integrals and functions of X to model the concrete. And we got, for this exact beam, 418.2 kip feet as our nominal flexural capacity. Here, today, we have used, which I would think nobody would argue, a much simpler method to come to the same answer. It's using the Whitney stress block, which is built in right here is the Whitney stress block, got you the virtually identical answer with a far less work. Okay, so that was my overall point, is how great this is. It's a lot easier than what we did last time. And now you can look back on last lecture and say, why did we do all that work? Well, you don't know how good you have it until you see what it could have been like. Okay? Now, to the question at hand. Why is this 6 KSI? The equation, let's go back to the equation for a second. The equation for MN for singly reinforced concrete, AS Fy D minus AS Fy over 1.7 F prime C B. AS Fy is 189.6 kips. And here's your 60 KSI for the steel right there. This 60 KSI is dictated by this grade 60. This grade 60 means that's 60 KSI. The concrete strength is 6,000 PSI. So this is F prime C down here, but I didn't want to intermix units. This is PSI, this is kips. If I put 6,000 in here, you're gonna get all messed up.
Yes, thank you.
Okay, great. Any other questions on this example?
Professor?
Yes.
So pretty much from last lecture, the first two parts, one was like not cracked and then cracked, and then we had the ultimate strength level. This one, this example, is pretty much our last example 6. We're doing the ultimate strength level of the concrete now.
Exactly right.
Okay, perfect. Thank you.
Yes. Uh-huh. Now, it's not inherent in this problem. It does not show up in these numbers at all. But all of this is predicated, it is assumed that the concrete at the top of this beam is at 003. It's just about to crush. And this is the maximum flexural strength you can get out of the beam just before that concrete crushes. Okay. Now we're going to look into some derivation of beam expressions. We're going to develop some tools that will help you design beams. Actually, let me go back here just a second. Let me talk about another term real quick, because I don't recall if I wrote this down anywhere. This problem here is what's known as an analysis problem. It's an analysis problem because everything is given to you. You have the strength of concrete, you have the number and size and grade of the steel, and you have all the dimensional properties that you need. So all you're doing is taking this and analyzing what the flexural capacity is. We're going to go into a whole nother realm of design. So you have analysis and you have design. When you design a beam, something will not be known. And in some cases, multiple things will not be known. For example, maybe all of this is given to you, but we don't know how much steel you need. Or maybe all of this is given to you except for D, and you don't know how much steel you need. So we're going to go from the simplest, which is analysis, to design. Now, again, please keep in mind that every design problem is going to end within an analysis problem. Every design problem, you're being called upon to design the beam. And once you come up with a design, the last thing you have to do is the analysis to make sure that you have sufficient strength. And we'll have lots of examples to show that. Okay, so derivation of some beam expressions. If we define the reinforcement ratio, rho, Greek letter rho, as rho is equal to AS divided by B times D, the ratio of the area of steel to the area of concrete, then solving for A, remember A was ASFY over 0.85 F prime C, BD. Well, if I substitute for AS rho into here, now we have A is defined as rho FYD over 0.85 F prime C. Solving for AS, I just rearranged this equation. AS is equal to rho BD. And we're going to again talk about this next lecture, but we know that phi min has to at least equal mu, the required capacity, and phi is the phi resistance factor to be covered later. Then phi min is equal to phi ASFY D minus A over 2. This is just the equation I just gave you, except for I put a phi factor in front of it, which is then equal to phi rho BD Fy D minus rho FYD over 1.7 F prime C. And then I see there's D and D, so I pulled the D out front. Phi BD squared Fy rho, 1 minus rho Fy 1.7 F prime C. All of this has to equal mu. Now, I know what you're thinking. Where is he going with this? We're going to get to something useful. If I define this new factor, R sub n, is equal to mu over phi BD squared, if I make that my definition, then I can substitute this back into this and solve for rho, and rho equals this expression. Rho is equal to 0.85 f prime c over fy, 1 minus square root 1 minus 2rn over 0.85 f prime c. Okay, so this is my final answer. This is your tool to put into your toolbox that will help you solve or design beams when you don't know how much steel you need.
Professor, so could you go back to the?
Yep. There.
So this is. So this value, what is it called? It's the ratio of steel to concrete. What is it called again?
Rho?
Oh, rho. Okay.
Yeah, RHO, rho.
Okay. And this value is the amount of steel we need, right?
It's gonna, yeah, it will lead to, because if you solve this,
right,
that gives you rho. And then if you want to know how much steel you need, you just multiply that times BD, and that'll give you the area of steel.
right.
It also allows, what you're going to see is it allows this to be put into tables. So we're going to have some tables at the back of your textbook that will do the same thing far simpler, a lot quicker.
Okay.
And this Rn factor is really like a load index, because it's the load, there's your factored moment, divided by phi BD squared. So it's like an index of how highly stressed this beam is based on the load.
Okay.
Okay. So let's do a quick example, design problem. So now what we want to do, here's my beam again, same beam as before, but now I don't know how much steel I need. So I need to find the required steel to support a load, a factored moment of 375 kip feet. I have the same parameters. F prime C is 6,000 PSI. My steel is grade 60. And for now, I'm just telling you that phi is equal to 0.9. And we'll work on that in a little bit. Solution. So I start with Rn is equal to mu over phi BD squared, which is equal to 375. I want to put in my 12 inches per foot in here, get everything in kips and inches. My phi is 0.9. My width is 18 right there. And D is 27.5 right there squared. This equals 0.367 KSI. So my equation that I just presented for rho, I can take the 0.367 KSI, plug it into here, and plug in all my concrete and my steel here and here, and I get a rho of 0.00635. When you're doing this, please run these out to 5 digits. Don't round this off to 0.006 or 0.1 for that matter. There's a huge difference in the amount of steel you need if you rounded this up to 0.1 as opposed to 0.0635. Okay, so just a side note, carry this out at least 5 digits. Since AS is equal to rho BD, so I have rho 0.0635 times 18 times 27.5, I need 3.15 inches squared of steel. I choose for number 8s. AS is, now, also, it's kind of hard to regulate this as you're going through all these examples, but this AS is my required AS. This AS is my provided AS. You kind of have to just get used to these problems and see the context. But this AS came from the equation that came from the demand. And then if I choose for number 8s, then the actually provided AS is 4 times the area of a number 8 bar, which is 3.16 inches squared. Okay. Here is where many students in the past have fallen a little flat. They said, okay, I choose for number 8s, and I get 3.16 inches. That's more than 3.15 inches squared. Therefore, I'm good. I'm done. Next problem. And not necessarily so. You always, always, always recheck your answer. And so you plug everything back into this, and the 3.16 is what we just did in example 1. So I'm not going to recalculate ASFY again. These are all the same numbers from the same area, but I get 376.4 kip feet, which is more than 375, just barely. So my beam is okay. Okay.
Professor, in practice, will you know the feed to be 0.9 that way, or?
It most of the time is.
Okay.
Yeah, most of the time is. Okay, how do you know to start with the Rn equation as opposed to the rho equation? Well, if you start with the rho equation, you can't go anywhere because you don't know what Rn is. Rn is in the rho equation. So you have to start with Rn.
Professor, and
Yes.
since we did 4 of them, 4 ASs, is that because in the drawing there's 4 of them? Like, is that like
No.
given you have to use 4?
No, it's not. Not at all. Good question, but no. Remember, these drawings are always symbolic. And I did not have to use 4 number 8s. I could have used 5 number 7s. No, 5 number 7s. I could have used 6 number 7s. So 6 times 0.60 is 3.6 inches squared. That would have worked. And let's see, I could not have used 3 number 9s. I could have used 3 number 10s. 3 times 1.27, and that would have worked as well. So you have choices. You could have used 6 number 7s, 4 number 8s, or 3 number 10s. And any one of those 3 answers would have been equally acceptable because each one of them would have given you a strength greater than what you needed. Did that help your question?
Yes, thank you.
Okay.
And does that fall down to economical choices for which
Yes.
one we pick, or?
Yes, it does. And it also falls into engineering judgment. There's just some choices that make a little more sense and others don't. But the bottom line is it's a design. You as the designer can make that choice. That's the bottom line. And there's more than one right answer, which makes my job very difficult when I grade your homeworks. There is more than one right answer. I have another question. When you pick the number of bars, what do you do if you have an odd number of bars? It doesn't change anything if I have an odd number of bars. They're all in the same layer, so they're all at the same D. So all I would do is instead of 4, I put a 3 right there. And instead of 0.79, I would put 1.27 for a number 10 bar, and I get an area of steel. So odd number of bars, even number of bars doesn't make any difference at all. If they all fit in the same row, then it's just a total area of steel that matters.
Professor, could you just quickly again explain how you made your choice?
Well, I knew I needed 3.15 inches squared here. So I chose a solution that gets me as close to 3.15 as possible.
Okay.
So I kind of just, it's either going to be 6 number 7s, which is 3.6 inches, or it's going to be 4 number 8s, or it's going to be 3 number 10s. And I didn't actually look at 3 number 10s, but 3 times 1.27 is 3.81. So of those 3 choices, the 4 number 8s got me closest to what I was looking for.
Right. So let's say you put it in the equation here, and you get an answer less than 375.
Here, less than 375?
Yeah.
Okay, well that's fine. It just means
okay.
it ain't gonna work. So you gotta try again, pick another solution.
Right.
Which happens all the time. It actually happens all the time. And that's why you have to recheck your answer, because there may be something else in here that changed a little bit. For example, what if this area of steel was so large that you couldn't fit it all in one row? Then you have to put it into 2 rows. Well, when you put it into 2 rows, D is measured to the centroid, so D gets a little smaller, and that would fall into here. And so you may have more steel than what row told you to have, but because you lost a little effectiveness on your D, you might still be falling short. That's why we do this last check.
And Professor, how did we use the 3.16 in this last equation?
I skipped that step. The
Okay.
3.16 was the same as example problem number 1.
Okay.
And so AS 3.16, so basically 3.16 times 60 equals
Would be-
189.6 here and here.
And Professor, I have a question. So for design problem, we'll have to start off with an assumption on what steel we use, right? So we have our Fy in the row equation. If not, we're not able to plug in the Fy.
That's correct. Yes.
So you always start off with assumption first, and if it doesn't work, then you adjust the sizing, correct?
Let me reword your question just a little bit.
Okay.
Design problems always start with either one thing is unknown or more than one thing is unknown. And if it's more than one thing is unknown, then usually something will be given to you to relate the unknowns together. So always there will be enough information that you can solve it. But you have to kind of think a little bit. And what happens is these equations, you might have to work them backwards sometimes as well.
Okay, thank you.
Okay. So let's see, ductility. Oh yeah, this is a whole another very important section. Why don't we take a little break? I still got about halfway done, so that's not bad. Let's reconvene at 6:15. How's that? Okay, so
Perfect.
I'll be back at 6:15. Thank you. So we still have a minute or two for folks all come back. So how's everybody doing with virtual learning during this summer?
It's all right.
Miss going to campus.
Yeah, yeah. I feel the same way. It's just not the same as, being in the classroom and having face-to-face interaction. But I guess it's better than, everybody's career, academic or whatever, just being on hold until this whole thing is done.
Yeah, it's better than the whole shut off for a few months.
Yeah. Yep. Anybody know when we're going to be able to eat at a restaurant again?
I heard some of the restaurants open, but like they have to follow certain measurements, like certain measures.
Well, before the protest, it was supposed to open today, but I don't know if
Yeah.
that has delayed any phases.
Yeah, the cases went up because of the
Yeah.
protests. So now we're literally back to square one.
Oh,
Did
We're
they-
supposed to hit phase 3 today, which is reopening of everything.
yeah.
Since the protest, I believe it has shifted back. So,
But did they announce that it has shifted back? Like did they?
it wasn't announced, but the curfew. Have you guys received the Amber Alerts lately about the curfew?
Yeah, the curfews was because of the protest.
Yeah, but then it hasn't shifted officially. But some restaurants have chosen not to open because of the
Oh.
protest. So we're not sure on that.
I see. And are you guys, I mean, not getting personal or anything, but are you guys talking about like LA County or San Bernardino County, or does it matter?
LA County.
LA County.
Yeah, LA County. I heard that there's a bunch of restaurants that are actually open right now, so you can dine in right now, I believe.
Oh, okay.
But
All right.
yeah, only certain cities, I guess, that they propose that, I guess. But I know that like in the Downey area, there's a couple restaurants that are, for dine-in.
Oh, okay. Okay. So it should start like in the next week or two, start opening up some things,
Hopefully.
hopefully. Okay. Well, I still got a lot of ground to cover. Sorry, but we got to talk about concrete. So if everybody is back and awake and refreshed, then let's move on. We're going to talk about ductility requirements and the 3 failure modes that a concrete beam could experience. And this will explain why the code is so prescriptive about how much steel you're going to have and the maximum amount of steel and a minimum amount of steel that you can put into a concrete beam. So the 3 possible failure modes: you could have a lightly reinforced beam, and the danger of too lightly reinforced is members can fail suddenly if the nominal flexural capacity Mn is less than M cracked. Remember last lecture we talked about M cracked. If the capacity of the beam is less than the cracking moment, then once the beam cracks, it will also and suddenly fail. So in other words, say like you have a beam that has just a little bit of rebar in it, and the design strength of that beam, like we just did in our example, is only 100 kip feet. But we can also figure out from the procedure we did last time that maybe it takes 150 kip feet to crack that beam. So what happens if you put 160 kip feet on this beam? It will crack at 150, and the moment that it cracks, it instantly doesn't have enough strength to carry it, so it fails. So as soon as it cracks, it's on the ground. It has failed. And that we cannot have. That's a brittle failure that has no warning. So that is not allowed. So here's a representation of a beam with a little bit of rebar, and that is not allowed by code. And so to prevent that, ACI 318, section 9.6.1.2 specifies minimum steel for beams as AS minimum is 3 square root F prime C over Fy BWD, or, and it's the greater of either of these two, or 200 over Fy BWD. This 200 right here is in PSI. The 3 square root F prime C is PSI. So in these equations, you have to use 60,000 PSI, 60,000 PSI in order for the units to work out, whichever is greater. BW, or B sub W, as is defined as the beam width for rectangular beams. So that just be this width here. And for T-beams, which we haven't got to yet, but for T-beams, it is the lesser of the width of the flange B sub F or the width of the web B sub W times 2. So kind of just keep this in mind when we get to T-beams. ACI 318, section 9613 allows the minimum steel to be waived if AS provided is at least 1/3 greater than needed by design. So they're basically saying that as long as you got enough strength to be 133%, then we can forego these minimums. The next failure mode is what's known as under reinforced. And so I've got more steel now. Under reinforced is allowed and preferred by code. So this may sound bad, but under reinforced is good. Under reinforced is what we want. Based on the strain diagram, rebar will yield prior to the concrete reaching its ultimate strain of 003. This is what we want. So here's my strain diagram again. My concrete is at 003 inch per inch, and epsilon sub s here is more than 003. Epsilon sub s is enough to be sure that this rebar is going to yield. Rebar yielding first is good. When the rebar yields, it causes the beam to crack and deflect, giving plenty of notice of an impending problem. Okay, so let me go back to this for a second. Under reinforced is good. That's what we're aiming for. Too little reinforcement, like we said a minute ago, that's not the same thing as under reinforced. That's not enough reinforcement. But under reinforced is what we are striving for, as opposed to over reinforced. Now that's why I'm making a big point about this, because it's kind of contrary to logic, really, common sense. You say, well, you want the beam to be stronger than the demand, so more reinforcement is better, right? The more reinforcement is more strength. No, that is not what we want. Over reinforced, and here I'm showing it with a whole bunch of steel, is not allowed by the code and is very dangerous. Based on the strain diagram, rebar will not yield prior to the concrete reaching its ultimate strain of 003. Okay, so here's how it works. If I've got a whole bunch of steel, then the tensile force, ASFY, is a big number. If the steel is a big number, then that means the concrete has to equalize it. I have to have the same big number in the strength of the concrete in compression, which means dimension A gets very big. If dimension A gets big, then dimension C gets big. The distance to the neutral axis gets very large. If C is large, then through the strain diagram, epsilon s gets small. That's bad. If epsilon s is less than yielding, this is a very dangerous beam. This presents a dangerous situation where the beam capacity is limited by the strength of the concrete. If the beam fails, it will be sudden and explosive. ACI 318, section 9331 prescribes the minimum strain for beams. This doesn't apply to columns, but for beams, the minimum strain for epsilon sub t as 0.004 inch per inch. ACI 318 table 21.2.2 puts a penalty on designs where epsilon sub t is less than 0.005 inch per inch in a form of reduced fee factor. If epsilon sub t is less than 0.005, then table 21.2.2 prescribes that phi is equal to 0.65 plus 0.25 epsilon t minus epsilon sub ty over 0.005 minus epsilon sub ty, where epsilon sub ty is equal to fy over es. Epsilon sub ty is the yielding strain for your rebar. Okay, that's a lot of stuff in one slide. Do we have any questions?
Professor?
Yes.
You kind of lost me on why over-reinforced is dangerous.
Okay. We want the rebar to yield before the concrete crushes. When rebar yields, it's not actually a failure yet. When the rebar yields, what happens when rebar yields is the beam will deflect and you'll have lots of cracks, and some of those cracks will get big and scary. And it is obvious to anybody who can see the beam that, oh, there's too much load on that beam. We got something going on here. It's deflected, it's cracked, it doesn't look good at all. We need to fix this thing. That's what happens if the rebar yields before the concrete crushes. What happens if the rebar does not yield and the concrete crushes first? If you had an overload situation, which can happen for any number of reasons, there can be an overload situation. If you have an overload situation and the rebar does not yield, then all of a sudden, and I mean all of a sudden, that concrete crushes and whatever that beam was carrying, it all comes down to the ground. Okay, so does that part of it make sense?
Yes, it does.
Okay, so the concrete beam is always going to fail because the concrete crushed. The only difference is, did the rebar yield before it crushed, or did the rebar not yield before it crushed? I'll say that again. All concrete beams fail when the concrete crushes, which is this definition, 003. But the difference between under-reinforced is the rebar will yield before you hit 003, and over-reinforced, the rebar will not yield before you hit 003. So under-reinforced is good, and that's what we're aiming for. Over-reinforced is dangerous, and we're steering away from that. Does that all make sense?
Yes, thank you.
Okay. So that's the philosophy. That's the goal of what we're trying to do. How the code makes you do that is you have to check epsilon sub t. And when you check epsilon sub t, if it is more than 0.005, then your phi is 0.9. But if it is less than 0.005, but more than 0.004, then you use this equation, which is a linear interpolation, to get your phi factor. And thirdly, if it is below 0.004, your beam is not okay. You have to start over with a new design. The code will not allow you to do what you're trying to do. Okay?
Professor, you said if our sorry, P is below 0.05,
Yes.
then we use this equation.
Yes. Yes. But this is epsilon sub t.
Right.
Okay. So if epsilon sub t, you have three possibilities. Think of it this way. You have three
Okay.
possibilities. Epsilon sub t could be greater than 0.005, then phi is
Right.
equal to 0.9. Epsilon sub t could be between 0.004 and 0.005. You have to use this interpolation, which is going to get you something less than 0.9. Or the third possibility is epsilon t is below 0.004, in which case your beam doesn't work. You have to start
Okay.
over.
Okay.
Okay. Okay. And then I some of this I wrote out, so it just kind of reinforces
Okay. Yeah.
what I said.
Yeah. It wasn't there, so I was okay.
Yeah, yeah. I tried to put the bow on it. I haven't finished the slides yet. But okay, so if epsilon sub t is greater than 0.005, then phi is equal to 0.9, and that's fixed. It never goes higher than 0.9. If epsilon sub t is less than 0.004, the beam is not allowed, thus limiting the maximum reinforcement a beam can be designed with. So in other words, the code doesn't say, here's your limit. You can't go higher than this. What the code says is check epsilon sub t. And if it's less than this value, well, now you have too much steel. Okay.
Professor,
Yes, yes.
what again does 0.005 represent?
It's a threshold. Steel, normal 60 KSI steel yields at 0.0207. So somebody decided we're not going to set that number right at 0.0207. We're going to have a safety factor in there. So somebody just decided, you know what, let's make it 0.005. That sounds safe. And that's just, it's a number that the code committee came up with that we must abide by.
Oh, okay.
Mm-hmm. And if you have the chance, go back and review this document. And in slides previous to here, I give you the sections of the code that dictate that 0.005.
Okay.
Okay. So now you might say, okay, well, that's great. How do I figure out what epsilon sub t is? Well, to determine epsilon t, we use similar triangles. So here's my strain diagram. D is from the top of the beam to the rebar. Epsilon sub t is at the rebar. C is from the top of the beam to the neutral axis, and my strain is dictated to be 0.003 at imminent failure. So using similar triangles, I can say epsilon sub t plus epsilon cu over d is equivalent to epsilon cu over c. So in other words, this triangle is equivalent in proportions to this triangle here. Actually, I can draw that a little better. So there, that triangle, that triangle, that triangle. So that triangle is similar to this triangle right there. Okay, so by similar triangles, that epsilon t sub t plus epsilon sub cu, which is this length and this length together, so those two together is this whole horizontal length, over d is the vertical distance, is equivalent to epsilon cu, which is this length, over c, which is this vertical distance. Okay? So those two are equivalent, so then we can refine this, and we can say epsilon sub t is equal to D epsilon Cu over C minus epsilon Cu. Or we can say is equal to epsilon Cu D over C minus 1. And epsilon Cu is 0.003. So epsilon sub T is 0.003 D minus C over C. This is, you can use any form of these equations, but this is the one I'm going to use. So you have to know what C is, and you have to know what D is in order
Professor,
to find that. Yes.
sorry, the epsilon U is supposed to be epsilon of the concrete, epsilon Cu. Up top, the epsilon U. Yeah.
Okay. Yes.
Okay.
Sorry, I didn't try. I tried to be pretty strict about this, but occasionally these will be a little bit different. This is ultimate strain. That's what this is supposed to mean. U is ultimate, epsilon is strain. So ultimate strain. And then this means ultimate strain in the concrete. Ultimate concrete strain. It's the same thing.
Right on. Thanks.
Okay, no, and that was a good question. Please question me on things like that. I'm trying to be more consistent. Concrete is not the most consistent stuff in the world, but I'm trying to make this more consistent. So by all means, please ask me questions about things like that. But in this case, this and this are equivalent. They're the same number. So here's our value. And there is, by code, no maximum value for epsilon sub T. So per the code, there's no limit on how far the steel can strain, because the steel is never going to be what fails. It's always going to be the concrete that fails first. If epsilon sub T is less than or equal to the yielding strain, then we say that this member is compression controlled. And we're going to get back to that when we get to our column designs. If epsilon sub T is between the yielding strain and 0.005, this is a transition region. And this is where we use our linear interpolation. If epsilon sub T is greater than 0.005, then we say that it is tension controlled. And compression controlled, transition region, tension controlled, all have very distinct meanings when you're talking about the phi factor. Okay, guys ready for an example, or do I have any more questions before we start? Okay.
Go back a little bit for that one.
I'm sorry, I heard somebody.
It's like, I got the other side. I got it.
Professor,
okay?
where
Yes.
does when does the epsilon sub S play a factor? Because I know that since we have only one row of rebars here, that's why the epsilon T is the same as epsilon S.
Yes, that is
But
correct.
But how does the epsilon S play a factor here, or it doesn't?
It really doesn't.
Okay, got it.
It
Thank
doesn't. And and again, that's a great question. We're going to get to compression steel, and we're going to have epsilon S prime, which is the strain in the compression steel. And that does matter. That one we have to solve for. But because the tension steel, not the compression steel, the tension steel always has to be yielding for the reasons that I just explained, then epsilon S doesn't really matter, only epsilon sub T.
Thank you so much.
Okay. All right, so let's look at example 3. We want to find the phi factor and check maximum reinforcement. So here's our beam, starting to look kind of familiar, 18 inches wide, 30 inches deep. And I've got 6,000 PSI concrete, and I have my 4 number 8s, grade 60. Solution. My area steel, 4 times 0.79, 3.16. Tension is ASFY, 3.16 times 60, 189.6. D is 27.5. B is 18. A is ASFY over 0.85 F prime CB, as we just talked about a little bit earlier. So A is ASFY 0.85 F prime C B equals 2.07 inches. C is equal to A divided by beta 1. So beta 1 for 6,000 PSI concrete, we can either look it up in table 8.7 or we can use this interpolation. So for the interpolation, it's 0.85 minus 0.05. My F prime C goes here, 4,000 over 1,000. I get 0.75 for my beta 1. So C is 2.07 over 0.75, which is 2.76 inches. Therefore, epsilon sub t is 0.03 d minus c over c. So 27.5 minus 2.76 over 2.76 is 0.0269 inch per inch. 0.0269 is actually much greater than 0.05, so this beam is perfectly fine. Epsilon t greater than 0.05, therefore phi is 0.9. Okay, and that was the end of that example. So any questions on that? And I do know that I have some other examples, either this lecture or next lecture, where it's not always greater than 0.05. So I'll show you what to do if you fall below that threshold.
Professor, that 0.003 d minus c over c, that was that similar triangles example, right? Or that what you showed us?
Yes.
Okay.
Yes. Yeah. So you don't need to do the similar triangles every time. This relationship is valid, so you can just use this equation.
So Professor, here what? So D is, oh, okay. C is the distance from, like from the beam to the steel, right?
D is always going to represent top of beam to the center of the steel.
To the center, okay.
Yes. C always represents from the top of the beam to the neutral axis.
Okay.
Okay?
Where you said C from the top of the beam to the neutral axis.
Yes.
Shouldn't that be more than 2.76?
Nope. Let me go back right there. Okay? Concrete 003.
Right.
C is from the top of the beam to the neutral axis, and D is from the top of the beam to the center of the steel.
Right.
And so in the example that we just did, C is 2.76 inches. Does that
Okay.
bother you?
I was just trying to figure out how did we find it to be 2.76?
Yeah, yeah. But that's actually not uncommon to have a small number, because if you look at the previous examples, because this is the same beam, right? So
Right.
the load was 189.6 kips for those 4 number 8s.
Right.
And if you take 189.6 and divide by the width and divide by the stress of 0.85 times F prime C, it's not a big number.
Right.
It doesn't really take a whole lot of concrete to balance that steel, which we did right there, 2.07 inches. So it just kind of hitting home this point here. With 6,000 PSI concrete, then 18 inches wide by only 2 inches deep is all you need to develop 189 kips. And that's what balances the steel.
Okay.
And yes.
Go ahead. No, go ahead.
Well, I was just going to say, so A is 2. So we found by calculation that C is 2 3/4, basically 2.76. So the neutral axis is very close to the top of the beam.
Oh, okay. Okay. This is okay, because I just imagined in my head that the neutral axis is going to be somewhere in the middle.
Ah,
Yeah.
but it's not.
Okay. Yeah. This is okay.
Now, if you took the same beam and you did what we talked about last time, where we found the cracked moment of inertia and you
Right.
solve for X, that's going to be much deeper. I think X was like 7 inches or so. But that's only because we're looking at elastic properties. Now we're looking at plastic properties, and the neutral axis goes way up higher when you're talking about plastic properties.
Right. Okay.
Okay. And so C is so small, that's why epsilon sub t is so big. Because the triangle is very lopsided. It goes way out because the neutral axis is fairly close to the top.
Professor, so the neutral axis is just where there's no stress or strain in the concrete, right?
That is right.
Okay.
Yep.
Professor, I might have missed earlier, but when that epsilon t criteria is met, where it's greater than 0.005, you can make the assumption that phi is 0.9.
Yes.
Okay.
Yes. That was just a couple slides before. So if you want to review the presentation, that was around slide 170 or so, somewhere in there.
Okay. Thank
Yeah.
you.
Mm-hmm. Okay. We'll talk for a few minutes about reinforcement placement. There are some guidelines and some rules about how you can place your reinforcement. So the first thing that we talk about is clear cover. Clear cover determined by design. So clear cover is defined as how much concrete do you have outside of your steel. And in this case, it's measured from the outside face to the outside of the shear ties. So the dots in here, the circles, is your main flexural reinforcement that's running longitudinally down the length of the beam. This tie here, this hoop, is a transverse piece of steel. And these are placed along the length of the beam at a certain spacing. We'll get into the shear design later and the purpose of these ties later. But suffice it to say that concrete beams are built with your flexural steel and a shear steel wrapping around it. Did I have a question? Okay. If you have a question, just jump right on in. So we can't build reinforced concrete beams with the steel exposed. That's just not good. That it just looks nasty, because steel has this really pesky habit of rusting when it gets into moisture or exposed. So we have a certain amount of coverage of concrete all the way around to cover up that steel. Typically, the coverage is taken as 1.5 inches, but may be influenced by code requirements for corrosion protection or fire protection. This little buffer of concrete around here keeps the moisture from attacking the rebar, but it also keeps fire from heating up the rebar too much and failing the beam too quickly. So there are other code requirements for how much coverage, but typically 1.5 inches is very common, where this thickness of this layer of concrete is 1.5 inches to the outside of the tie. Side cover typically is the same as the bottom cover unless special conditions require something special. So 1.5 inches here, 1.5 inches here, here, and here.
Professor,
Yes.
Is this typically found maybe in like the specs portion or something of a project where they'll tell you specific clearance size?
I would not expect it to be in the specs. I would not expect it to be there. I would expect it to be on the structural drawings that actually detail the beams.
Okay.
Or, I mean, what we usually do, a lot of times what we do is we just pull a dimension on the side and we say 1.5 inches clear or 1.5 inches cover typical. and then that applies everywhere. I suppose it could be in the specs, but I'm used to seeing it on the structural details.
Cool.
So the side clearance, center of the first rebar to the outside of the tie, so center of the rebar to the outside of that tie, can be taken as larger of half of the size of the rebar plus the thickness of the tie, or 3 times the diameter of that tie. And the reason why you have 2 is you can picture if this bar is fairly small, it sits right in that radius as I drew it. But if this bar is big, it will push right up against the side. So it's whichever one of these is larger, where dB is the diameter of the flexural steel, dBt is the diameter of the transverse or shear ties. Rebar clear spacing, ACI 318 section 2521 prescribes minimum clear spacing inside face to inside face of rebar in a single layer as the greater of 1 inch or the diameter of the bar or 4/3 times the diameter of the aggregate, which is kind of hard to know if you're not the concrete mix designer. But usually what happens is you design it based on these 2 criteria, and then somebody will size the aggregate appropriately so that it fits. But the whole issue is you got to get your rocks in your sand, in your rock, in your concrete mix to come through the rebars and fully contain all the way around these layers, where DAG is nominal maximum size of the coarse aggregate. Rebar clear spacing vertical, ACI 2522 prescribes the minimum clear spacing of rebar between layers as just 1 inch. And the ACI also says you got to stack your rebar so that they're one on top of each other if you have multiple rows, because you don't want the aggregates getting hung up on the rebar and not making it to the bottom of the beam. Okay. All of this seems kind of cumbersome or complicated. I think we're going to have a homework assignment where I ask you to do this once so you can see how it works. But we also have table A.5 on page 597 of the text, gives a summary of required minimum widths of beams to accommodate number and size of flexural steel. And I find that to be very useful, because you may have a design where you say, well, I need 8 number 10s in a 14-inch wide beam. You can only fit 3 number 10s in a 14-inch wide beam. So you need this reference to know if your solution is practical and buildable or not. Any questions on this?
No.
Okay. ACI section 20.6.1.3 provides prescriptions and tables that dictate minimum concrete cover for corrosion protection. Additionally, ACI 318 section 19.3 gives some concrete mix requirements based on exposure. So in the simplest way, there's tables in this 26.1.3 that say for cast in place concrete, for precast concrete, and for pre-stressed concrete, I believe, there's different requirements for coverage. And it also depends on your exposure. If you are pouring concrete right up against dug earth, you need more coverage. If you're exposed to weather or rain, you need more coverage. And if you're in ideal conditions inside of a structure, protected from the weather, and you're using a precast beam that's made under plant manufacturing tolerances, then you would need the least amount of coverage. So that's how that works. Okay, example number 4. Find the allowable flexural capacity of the following beam. So here we got a beam, and it's 18 inches wide, 30 inches deep. I've got 3 number 9s, 3 number 10s, and I've given you the distance d to each layer as 25.19 and 27.38. F prime C is 3,000. Steel is 3 number 10s, 3 number 9s, grade 60. Solution. So I need a total area steel. So I look up in the back of the book that a number 10 is 1.27 and a number 9 is 1.0. So my total area steel is 6.81 inches squared. D sub T is to the lowest layer, 27.38 inches. D sub T, distance to the lowest layer. A is ASFY over 0.85 F prime CB. I plug in the appropriate values. I get 8.9 inches for A. C is A over beta 1. Beta 1 for 3,000 PSI concrete is 0.85. You can go back to the previous slides to where we define that, or you can go to your textbook and look at the appendix. So C is 8.9 over 0.85, 10.47 inches. Epsilon sub T, here's the same equation. I plug in D sub T, not D, but D sub T. D sub T is 27.38 minus 10.47 over 10.47. I get 0.0485. Okay, notice this. This is between 0.04 and 0.05. So this is that transition area. It's greater than 0.04. So epsilon CTY is 60 over 29,000, 0.00207. So my phi factor, I plug in epsilon sub T, epsilon sub Ty, here, and I get my phi is 0.887. Now I need to know what my D is. This was D sub T. D sub T was to the lowest layer. I need to know what D is to the centroid of all of my steel. So I do a weighted average. I do the area of my number 10s at 27.38 plus the area of my number 9s at 25.19 over my total area. D effective is 26.42. Now my Mn, my nominal capacity, I plug in my ASFY, my effective D, ASFY, F prime C, width of the beam. And I get 8977 kip inch or 748 kip feet. This is my nominal capacity. My allowable capacity is times phi. Phi is 0.887. So my allowable capacity is 663.5 kip feet. This is my allowable capacity. So please note that if you're in this range between 004 and 005, you're kind of chasing your tail, because the more steel you put in there, the lower phi is going to be. The lower phi is going to be, the lower your answer is going to be, so you have to put in more steel. So you really don't even want to be in this area at all. The code just made like a buffer zone so that it's not absolute, yes, it works, no, it doesn't work. They gave you a little bit of a buffer zone, but ideally you want to be well above 005 and not caught into this zone here. Okay, do I have any questions?
Professor, so for the M sub N, we always use the D average. When we're finding E sub T, we use the lowest one, lowest for the D.
Exactly right, yes.
Okay, perfect, thank you.
Yes.
So could you repeat this idea, please, again?
I'm sorry, repeat what?
Oh, could you repeat this idea again of the M sub N?
M sub N here?
Yeah.
I'm sorry, repeat the part about chasing your tail, or just what this means?
No, no, like M sub n, like how the like using the average or using the minimum.
Or you want to say what I said again?
Yeah.
Okay,
Oh,
so
I'm sorry.
yeah. So for the M sub n, you use the D average.
Here,
And for the,
right there.
yeah,
Right.
Yeah, so
that's the D average.
this D is D average, which is to the centroid of all the steel.
Right.
Yes, that's exactly right.
Okay.
And then here, this D, in finding epsilon sub t, this D is actually D sub t to your lowest layer of steel.
Okay.
It's a complication that the code wrote. They could have just as easily said epsilon sub t is at the average of all the steel, and then all the D's would be the same. But then they felt, well, we're smart people. We can handle a D and a D sub t. I said, all right. So that's why there's a D sub t here to the lowest layer. And that's how you calculate epsilon sub t. Epsilon sub t is defined as the strain in the lowest layer, whereas the strength is, this is the total steel. So you need the D to the centroid of the total steel.
Okay. And then B was beta was given, right?
Beta 1 here?
Yeah.
Beta 1 was not given, no. But beta 1 was found to be 0.85, either by the equations or definition that I gave you in the previous slides,
Okay.
or by going to your textbook, page 598, table 8.7, and it says right underneath 3000 psi concrete, beta 1 equals 0.85.
Okay.
Professor.
Yes.
So I think someone just answered that question, or I think you asked someone. I think you answered it, but when you were saying that the D in the M sub n is the average, is that the average of the three D's that are on the right side of your drawing there?
No.
The average of those three, or
no, and I'm glad you asked that, but the answer is no. These are not 3Ds. I want to be very clear. Let's clear these up now before you get too far down the road. These are not 3Ds. This guy right here, this 2'6", that's 30 inches. This is not D at all. This is H.
that's the H. Okay.
That's H. That's the height of the beam. So this one doesn't count at all. This one is D sub t, the distance from the top to the lowest layer, D sub t. This one actually is not, I'm sorry?
The tension most layer?
The lowest most layer.
Okay.
Yeah, the one furthest away from the compression face, the lowest layer.
Okay.
So this one is D sub t, which I said right here, D sub t is 2738. That's the distance to the lowest layer. The 25.19 is not actually D at all. It's just the dimension to the upper layer. So D, again, thank you for asking the question. D is actually where the centroid of the 3 number 9s and the 3 number 10s, where that centroid is, D for your flexural strength is the distance from the top to the centroid. And we calculated that right here. Okay, are you still with me?
Yeah.
Okay, there's 2 Ds. In this problem, because we have 2 layers, well, no, not because we have 2 layers, because we have multiple layers, there are 2 Ds. There's D sub t to the lowest layer, and then there's D to the average of all the steel.
Okay. So D is just the average of the steel. It's not those three numbers on the side. It's the
That's
average of the steel that you have there. Okay.
Yes.
Okay.
And please don't make that mistake because these are not equally weighted.
I probably would have.
This would give you the wrong answer because what you would have done is said this plus this divide by 2. And that does not equal 26.42. And the reason why is these are 3 number 9s. These are 3 number 10s. They're not equally weighted. As you can see right here, 3 10s, 3 9s. They're not equally weighted. So the average of them is slightly lower than just taking these 2 and divide by 2.
Oh, okay.
And I did that very intentionally to make, to illustrate the point that D is not the average of these 2 numbers. And remember, this number has nothing to do with it. Let's do this, because that number is the height of the beam. So don't even look at that. That has nothing to do with nothing. But if you just took this number and took an average, you would have the wrong D, because I made these steels unequal. I made these bigger and I made these smaller. So you have to do a weighted average to get the true centroid of your steel.
Oh, okay. Okay.
Okay?
Yeah, thank you.
Okay.
If
Yes.
those were the same size, we can take the average of those 2 values. Is that correct?
Yes, it is correct, but I would rather you think of it this way than a special condition where I can just add the 2 together. I'd rather you understand why this is the centroid. It's a weighted average. But to answer your question, if they were 3 number 10s and 3 number 10s, then if you run this equation, you will get the average of these 2 numbers. Does that make sense?
Yeah, gotcha.
Okay. All right, we're pretty much out of time. If anybody else has any questions.
Yeah, Professor, when AS equals 3 times 1.27 inches squared.
Yes.
You might have answered this already, but where did we get the 1.27 from?
I got the 1.27 from the first lecture, or from the back of your textbook, or from the back of your code book. I'll give it to you very specifically. Do you have your textbook?
Yes.
Okay, great. So on page 593, it is table A.2.
Okay.
Okay, and I would bookmark that or put a sticky on that or whatever, because you'll be referring to that a lot. But on page 593, table A.2, the middle column says cross-sectional area inches squared. You go down the bar number on the left-hand side, and you see for number 9, 1.00, for number 10, 1.27. That's exactly where those came from.
Thank you.
You're welcome. Okay, any other questions? All right, then I will stop recording. I will upload this to YouTube, and we'll see you on Tuesday. Please keep in mind that I have another Zoom invite that I turn on at 4 o'clock, and that's for office hour. If anybody wants to talk anything over in more detail, just log into that Zoom meeting at 4 o'clock. I'll tell you though that if nobody comes on, if I don't have any customers, then I'll keep that open until about 4:30 or so, and then I'll go grab a bite to eat before I start this lecture. So just a reminder, if you need any further, if you have any questions about anything, I'll be on it, so just log in and we can chat. Okay.
Have a good weekend.
You too. Thank you very much. We'll talk to you all next week.
Professor, have a great day.
You too. Thank you.